Yeah.
Hello, good afternoon.
Hello.
Hello.
Ahmet, how are you?
Fine, fine. Our Minister Mustafa VARANK, how is everything? Fine.
Fine, thank you. How many participants are there?
I think we have also YouTube channel. Many of them is joining and checking from the YouTube channel is much more convenient actually. And also we have Zoom session. Again, thank you very much for joining our session. I will just start just simple introduction. Dear Minister, Geoffrey and other researchers, actually we opened our HPC conference in the morning and our program has a great interest and we have many participants actually. Even in the morning session there are too many people join. But our Industry and Technology Minister, Mr. VARANK, especially wanted to attend and greet you before the session of his advisor, Dr. Geoffrey. And actually, we are very pleased the increase in the efforts from the effort, Mr. VARANK, in high performance computing, and there are new possibilities in the field of some artificial intelligence and supercomputers. Actually, we consider ourselves as lucky because our minister, he has already published a paper in this area. It is very our honor actually, and with Dr. Fox, and we have a good research. He knows the research institutions, then what is the research and how we how improve the research, and we are very pleased with the increased efforts also in this field and new possibilities while he is in the ministry, and we see many opportunities, many progress in the field of research. And I don't want to talk too much, and actually I would like to present the Minister of Industry and Technology, Mr. Mustafa VARANK, to give his speech, and thank you very much for attending. And I will give it to you, microphone.
Thank you, Ahmet. Distinguished participants, welcome to the 6th High Performance Computing Conference, which is being co-organized by TÜBİTAK ULAKBİM and Yıldırım Beyazıt University and brings together, I think, more than 200 researchers. As the Minister of Industry and Technology, I greet all of you with my heartfelt feelings. My ministry is responsible for Scientific and Technological Research Council of Turkey, TÜBİTAK in short, which aims to develop science, technology and innovation policies. High performance computing is a critical and exciting technology thanks to exponential growth in data production. So if we want to shape the future in such technologies, this kind of events present great opportunities to share recent studies. Today, we have also Dr. Geoffrey with us. Dr. Fox is a distinguished professor of informatics and computing and physics at Indiana University. He is also director of the Digital Science Center. He held several positions at Caltech, Syracuse University, and Florida State University. He currently works in applying computer science from infrastructure to analytics in biology, pathology, sensor clouds, image processing, deep learning, manufacturing, network science, and particle physics. Over the years, he has supervised many PhD students, including Turkish ones. He was also my professor during my graduate education at Indiana University. We also worked together at Pervasive Technology Labs. I always remember Geoffrey with his visionary and inspiring approach. Dr. Fox, it's a great honor for us to welcome you in this event. Thank you so much for your active participation. I strongly believe that our young researchers will get a taste of your visionary works. Dear participants, as you well know, supercomputers are widely used in many fields. These range from rockets, cars, high-resolution images to artificial intelligence, machine learning, computational chemistry, and etc. This technology strongly supports new scientific discoveries and becoming even more influential in our lives. That is why Turkey gives utmost importance to its extensive use. Our key activities in this technology include the Truba supercomputer system, which is our national science e-infrastructure. This national high performance and grid computing center serves all researchers. Processing power number of Truba users and scientific output has been increasing regularly. About a decade ago, Truba had only 454 users. Now we have more than 3,000 users. This infrastructure allows researchers and industry players easy access to sophisticated systems. Let me give you some fresh example. During the COVID-19 pandemic, Truba has supported research for vaccine and drug development. Researchers of Izmir Biomedicine and Genome Center have sequenced COVID-19 virus strains by using Truba. In addition, many analytical studies of TÜBİTAK Defense Industries Research and Development Institute are also conducted in Truba. Our Informatics and Information Security Research Center, Bilgem in short, also develops cutting-edge research with software and hardware co-design to demonstrate high-performance computing. We are planning to upgrade Truba supercomputer. We are building our next generation data center at Middle East Technical University. We will launch it, I hope, next June. This new data center will provide many data services over open data. We are also making the use of international cooperation opportunities. Our new Truba data center will be a formal member of the European Open Science Cloud Association. As a pilot study, we will mandate open data requirements for polar research data. So this will allow climate science to provide more robust and updated predictions for new models. Similarly, other scientific cluster data will follow the same path to facilitate access to bigger and better data for researchers. While we are working on opening scientific cluster data, Digital Transformation Office of Turkey is focusing on improving open government data. As we are all aware, if we want to build smart systems and solutions, data is the only input that we need. And here, I would like to make special emphasis on open data, whether it is open scientific cluster data or open government data. As artificial intelligence and machine learning transforms all sectors, investments in supercomputing multiply the benefits for Turkey. In line with this, we also provide research funding opportunities via TÜBİTAK to further develop high-performance computing. We prioritize research studies that focus on solving complex problems in health, energy, aviation, space, automotive, and logistics with supercomputing. At the international level, we recently became a member of European High-Performance Computing Joint Undertaking. Here, we partner with Barcelona Supercomputer Center to build one of the top 5 fastest supercomputers in the world. With this opportunity, let me give you wonderful news. By the end of next year, our researchers will have access to one of these 5 supercomputers in the world. Thanks to this new system, you will get results much faster and have the opportunity to test both design and software in one of the fastest technology. And I am also happy to underline that as part of the Euro HPC, we also fund and participate in the joint research programs as well. As an example, we will be building Center of Excellence along with TÜBİTAK Ulagvi, Middle East Technical University and Sabancı University to train users and facilitate industry's access to supercomputing. What I am trying to say is that, as you clearly see, we have a holistic view on supercomputing. Our strategy covers all aspects, such as increasing investment on infrastructure, improving research grants, and training human capital. We aim to lead in frontier technologies by becoming a global competitive power. As such kind of events brings together our outstanding researchers in this field. Let me encourage you all to advance in this field with your innovative projects. Do your best to combine your scientific studies with practical industrial applications. I always emphasize that Turkey has a great potential on technology-based startups. We may even have unicorns from this group with groundbreaking global solutions. To conclude, I would like to thank all participants for their diligent and tireless efforts. I wish you all success, and I want to thank again Dr. Geoffrey Fox for joining this conference, and I want to say hi again, everybody, all participants in this program. Take care.
Okay, thank you very much. And we have a very good news, by the way, by having some joint effort with HPC in Europe, and also I follow through the ULAGPIM, and it is very good, and we have very good opportunities to join, and even to the US with Dr. Fox, actually, and we are very glad to hear about this news. And I would like to give microphone to Dr. Fox for his talk, actually. And again, we thank you, our minister, for joining the session. We are very glad to see here in this and join our conference. And I hope you are going to finalize.
I will listen to the presentation.
Good. Thank you. And this is also your area, and it is very good to hear, and you be joining the sessions. Thank you very much again.
We may write another paper together.
Yeah.
That's right.
Yes. Yes, please, Dr. Fox, and thank you again for joining the conference from United States in Indiana, Bloomington, and we have a presentation, and thank you again. And microphone with you, Dr. Fox.
Do you want me to start?
Yeah, if you want, yeah, and see, also okay.
Okay, can you see and hear me?
Yes, yes.
All right, let's get going. So, all right, so it's a real pleasure to see so many people. I first met at Indiana, or actually some of them at Syracuse and then Indiana. And now I came back to see you at Turkey a few years ago, maybe I forget now, 3 years ago. And it's a pleasure to give this talk here and see you all in the audience. All right, so we're going to talk about the remarkable advances in high-performance computing and deep learning, and why that implies we need both data engineering and data science. All right. So actually, I was pleased to see that Mustafa was in charge of the ministry, because an important feature of high-performance computing is that it is really thriving in industry. That's because it's actually incredibly useful. And then not only useful, it's actually essential to make progress. And actually, at the moment, we should try to do something about this, but it is not so easy, actually, to get, at least in the US, to get jobs in high performance computing in universities. But it's certainly the demand for HPC students and staff and faculty, faculty class people in industry is unlimited. For obvious reasons, it's essential infrastructure. I mean, it's a sort of trivial point. We're doing big data. Well, big data needs big computing and powerful computing. And so that demands high performance computing. And when I remember when I started working in parallel computing, and which was the sort of where HPC started, at that time we were advancing hardware, software, and algorithms. Now, software has always been thriving, or at least very active, because we never get it right. If you look at hardware and algorithms, they sort of move around. Today, hardware is pretty active because there are all these new AI chips being developed. And algorithms is incredibly active because of the advances in machine learning and deep learning. And those, of course, interact with HPC. And again, my background was originally parallel computing. All the big data problems are parallel, although they're a little different from simulations. In simulations, you have giant jobs. In big data, you tend to have a larger number of smaller jobs, each job of which is, however, parallel. All right, so that's some sort of a cosmic status. So I've more or less said this, but I want to now focus on another issue, which is the convergence of big data and simulation and HPC. And I think it's now reasonably clear that they're effectively are converged and should be converged. If we look at simulations, we know from Mustafa described you joining the European initiatives in this area, but what's called Exascale and the US initiative and corresponding other countries' initiatives is really emphasizes the importance of what I would call computational science. It also, the other obvious area is the use of graphics processing units and possibly new novel hardware for deep learning. So there was Geoffrey Dean, who invented MapReduce, who's at Google. He calls this systems for ML. Namely, when we're talking about big data, we need these large systems for machine learning. And I call it HPC for ML, but it's essentially the same idea, that we need HPC to make the machine learning run well. That's still not totally certain, but it's relatively clear that the same principles that you need to make simulations run well also make AI run well. And an area I've been working in is to try to see how to make the software stack for big data, which typically comes from Apache, run well with the simulation software. But an area which I will actually spend non-trivial time discussing is what I call machine learning for HPC, but also Geoffrey Dean called it systems for machine learning for systems. It's using machine learning or deep learning to make the computations run faster. And that's a hugely important area. And it is quite uncertain and a very active research area. This is a chart that nobody quite likes because it's too confusing, but it has a simple message that there is the issues are quite similar between simulations and big data. If you look at this chart, the things on the left do not have much parallelism. The things on the right have extensive, complicated parallelism. And you will find big data and simulations in both these areas. The things in the middle are actually the area we're making the most progress. This is where we're using GPUs to make deep learning run well. Those are, in an old language I used to use, regular problems. where the regularity makes the vectorization rather straightforward and the parallelization straightforward, and you can get very good performance. On the right, you have these messy things, which include unstructured meshes for the hardest possible simulations, which could be adaptive. But you also have big data problems with the same difficulty. The graphs are very important in big data, and graph analytics, such as mining for subgraphs, it has some of the hardest parallel algorithms and difficult to make run fast algorithms there are. Even topic analysis, latent Dirichlet allocation, it also has similar difficult features. So we have over here a mixture of big data and simulation problems, which are hard, which are really hard, tough algorithms, where lots of research has been done. In the middle, we have the heart of probably the most exciting progress, because there we're really in production getting good performance, both for simulations and big data. On the left, actually, we hardly have most of the applications are on the left, because these are the loosely coupled problems. These are, well, I mean, if you look at big data, the most simple parallelism is parallelism over users. Namely, you have 7 billion users in the, well, possibly in the world, and that gives you a parallelism of 7 billion. So an important feature of big data, it has natural parallelism, because a lot of the big data is aimed at very important consumer applications. You do see such types of parallelism in simulations, such as parameter sweeps, but it is not as dramatic as it is for big data. Okay. All right. So that just says we're really making progress. There are lots of similarities between data and simulation. We should try to exploit them. Here is an interesting picture which I like to show. It comes from a paper written at NeurIPS in 2015. And the only thing to notice about this paper is there's a red square in the middle. That is the deep learning or machine learning. And then around this red area, you have all these other capabilities that you need to make the system work. And so this is why I pointed out, said at the beginning, I want to do data science and data engineering, because the red is sort of the data science. It's the hard, parallel, deep learning or machine learning algorithm. The things around it are all the data engineering required to get the data, curate the data, and manipulate it to make it in a suitable, robust form to be analyzed by the machine learning. And we will come back to that at the end, because these are non-trivial. Because if you look at, for instance, the thing in the middle, it's largely C++ and Python. But the computation is largely C++, running with very high performance. These data engineering around it is actually largely Java. It's Spark and Flink and things like that, Hadoop. And we need to link those worlds, and we will describe some work we've been doing to link those worlds together. All right. So now let me come to look at what I called machine learning for HPC. This comes from a project which is actually just essentially finished, funded by NSF, which was aimed at developing parallel machine learning. And that one did a lot of what I consider the bread and butter, the high performance computing to make machine learning run fast. But recently we have sort of switched to doing this other thing, making machine learning make HPC run even faster. And I worked with a colleague at Rutgers University, Shantanu Jha, and we wrote a couple of papers. They're already out of date. This field is making a lot of progress. But I will review this for you now. So I won't spend any time on this paper, on this slide here, but I will take these three areas here. We divided the ways you can make machine learning, make HPC run faster into several different areas. The first is typified by what's well known from the past called auto-tuning. You can now do auto-tuning in a much more sophisticated way, and that's called improving the simulation, and by optimizing the configurations. Somewhat deeper is here, we're learning the structure, the theory, and the model. And the good examples of this is there's lots of papers which use machine learning to learn the potential. They can actually form effective potentials. That's all learned nowadays by machine learning. And there's a lot of different categories in that area. Possibly the most exciting is the last category, which are surrogates. Here we take, say, this exascale, let's take one which was done, exascale climate simulation. You actually replace that climate simulation by a neural net, which you train. You do some climate simulations, and then you train a neural net. And there is a famous paper, mainly famous to me because of its scurrilous title, called Getting a Speed Up of 2 billion. And they got speed up of 2 billion on climate, when I think you're interested in climate. And that they did that by training a neural net to reproduce the results of these large HPC simulations. And that can be done in all sorts of different configurations, depending on whether they're discrete or continuous variables. I heard Mustafa mentioned COVID. I'll point out we can use this to help do COVID simulations. All right, so here's this early work I did a while ago now with my colleague Vikram Jadeo, who is in nanoengineering. He is looking at ions trapped between electrolytic plates, and this uses a pretty straightforward neural net. So you run these simulations, which are run with MPI and OpenMP on a supercomputer, or the one at IU, Big Red 2, and it then takes a small, fully connected network, and it just takes the input. The simulations depend on 5 parameters. There are 150 output values predicted, and we just train. We just take actually around 5,000 simulations, which we use to train, and then that gives us a neural net, which gives extremely good results. Here you see at the bottom right a comparison between for one of the densities, which we're predicting, a comparison between the predicted value from the real simulation and the predicted value from the neural net. And this is, for this particular problem, you get very reliable answers. And here, we didn't get a speed up of 2 billion, but we did get a speed up of 1 million. I should point out that this is pretty interesting for education, because if you can now actually realistically use simulations of complex parallel simulations in education, then the students can get instant feedback. Because if you take your parallel simulation and train the neural net, then that neural net gives an answer which is a million times faster. In industry, this is being used today, but I heard a talk by General Electric, which builds, among other things, does aircraft engines, and their engineers are using this idea to allow interactive engine design. They think of the general principles they want to look at on a particular day. They run 200 in this training simulations overnight. Then they train the neural net on those 200 simulations, and then the engineer uses it for his interactive engine design. So this is really a transformation, because we've gone from waiting hours for a simulation to be able to get instant feedback for change. So we can tweak all these input. We'll feed here in the corresponding General Electric one, you would feed in as the input layer will be the parameters the engineer wants to change. Right, so that's one example. And here is this 2 billion paper. Comes from mainly from United Kingdom. And it actually is even more subtle. It uses a very complicated neural net, and it dynamically chooses that. It's actually using reasonably sophisticated artificial intelligence to choose the neural net to optimize its representation of the simulations. This needs a lot more work because essentially nobody else has done that. And it's the results have certain issues which strike me as slightly strange. But they actually did 10 scientific simulations. They trained it on actually one rather obscure one and then used that trained network to do these things like climate science with high reliability. Here is a different example of this general principle of using machine learning, and this is related to COVID, although I don't think this one here is particularly COVID. I just found this news item last September, a year ago, where this Hong Kong startup in silico medicine were able to use these trained neural nets to drastically accelerate AI-powered drug discovery. And that is being done today. For instance, my colleague Shantanu Jha, who I work with on this, he is using these same ideas at this very moment to cycle through potential drugs for COVID. And the idea is extremely simple. You're trying to find a drug with a certain property. So you design neural nets that map properties of the defining parameters of the chemicals into their actual properties of any type. And this is being done actually not just in drug discovery, it's also being done in materials science and manufacturing. So nowadays you can make huge progress in being able to predict a new material, what the property of a new proposed material is, or the property of a new drug, as long as you've trained these neural nets to be able to represent this. And this particular company claimed they did for $150,000 what would normally take 2.6 billion and 7 years, whereas they did it in a few weeks. So it's probably overstated, but I think it's actually quite important. I think we're going to see an enormous increase in the use of neural nets to work together with simulations. So here is another piece of work I did with Vikram on a slightly different problem, which were generalized. So if you look at what is a deep learning network, the deep learning network, you feed in some values, it goes into the network, and out pops the answer. So a deep learning network is actually an operator, and we know all sorts of things about operators because all my things I was taught about in physics or chemistry were all about operators, differential operators and quantum operators and things like that. So deep learning is just a new operator, and we can actually, you can summarize what we just discussed by saying we were able to, deep learning was able, as it's such a flexible network, it's able to represent lots of different operators. And this in some sense points out that deep learning is really a new theory. Namely, it gives you a new way of thinking about, say, Newton's laws. And let's look at this example here. So this is work I did again with Vikram and a student, JCS. And this shows here at the top, it actually is some simulations of 16 particles interacting with the Lennard-Jones potential, and their groups of 4 pictures here, which are the simulation running on the HPC machine, and four pictures here, which are the one from the neural net. So we were able to learn the simulation of these molecular dynamics. And the interesting thing about this learned operator is it is incredibly robust. Namely, it is able to predict forward in time a factor of 4,000 longer than the traditional the things you're taught in Applied Math 101 about numerical approximation to differential operators. Well, actually, though, when I was taught numerical analysis, I was told never to use complicated parameterizations. And here we have, and the neural net has 65,000 parameters. And of course, the original operator only had a few parameters. But if you look at the error, here we are up to a time of, this is a time step of 1,000,000, and you see the error is just flat. And whereas if we go to Verlet is the classic method, as soon as and this goes up to a time step of 4, which is 4,000 times bigger than the natural time step. If you just increase the error by the time step by 10, already the thing gives you bad error. The error is 10. It's just unreasonably big. And if you take a time step of 0.1, 100 times the correct value, you get errors at 10 to the 23rd. So this deep learning operator has different characteristics. So that's pretty interesting, because and these really further study, because we need to understand where we can use these types of networks. And this plot here, this thing here just goes through it I gave you, the previous was 16 particles with Leonard-Jones. This is just one particle with a variety of different potentials. And suffice it to say that the answers are they show exactly the same effects. These, you get these better results of being able to be valid for larger time steps for all these different potentials, including some pretty complicated potentials. Here is work I'm doing with James Glazier, who is a colleague at Indiana University. Some of you might even remember him because he was here when you were students here. And he does biocomplexity, and he has a software system called CompuCell 3D, which is able, for instance, for COVID to simulate the interaction of the virus, the human cell, and the immune system, the three important parts of the problem. And if you look at that particular task of trying to be able to model the interaction of, well, in this case, of viruses with tissues, but more generally with cancer and things like that, you have lots of computing. And we are trying to work already we have some progress in developing surrogates for the time-consuming parts of this problem. But there are also other things we can do here which are quite interesting. Namely, there is a very classical method which is used in, say, weather forecasting of data assimilation, which is, the idea is you have a simulation, you have some data, you merge them together to get better answers. And so machine learning enables you to do much more sophisticated data assimilation. And we believe that we can use deep learning to really be able to get much better models of the human tissue. All right, so if we summarize that section of the talk, it's this field is really promising, and its use is actually developed in some areas a lot: molecular dynamics, material science, and the drug-related areas. It's very well developed, but it is not nearly as well developed in, say, things like this work I'm doing with Glazier. We're also looking at trying to do it for epidemiology, and I'll show you some initial results there later on. And as far as I can see, and it has these various methods, which I only mentioned a few in detail. For instance, I already pointed out it's made a lot of progress with multi-particle potentials in chemistry, because there the progress is limited because the old method, the scale like the number of particles to the 7th power to be able to get the potentials correctly. But you can learn a neural net that does that, which will greatly reduce the computational complexity. You can also do autoencoders and things like that to learn collective coordinates. That's being used today by my colleague Shantanu Jha to study drugs. So you can then use these collective coordinates to guide the computation through phase space. Another one is where it's been used very successfully is in weather forecasting to represent microstructure. You learn the microstructure, clouds. Actually, an even more obvious example is computational fluid dynamics, where you have to typically make turbulence models to make progress. Well, those turbulence models can now be done much better with machine learning. I showed you an example of recurrent neural nets. I don't think there's been that much work in that area, but from our results, it looks encouraging. And as I say, there are lots of interesting research here. We're trying to work on how to learn the errors as well as the values. We're trying to learn how to minimize the number of simulations needed to do the training, to minimize the training set size, because probably the hardest part of this problem, we have to train. So in principle, we need to run thousands of simulations, which if they're exascale is quite time consuming. Now this 2 billion paper did something quite clever, which seemed to work, but it has to be verified. Namely, they trained on a simpler problem and then used that trained network on a complex climate problem. Whether how well that actually works in general just needs more study. All right, so now let's come to a totally rather different type of work, which was actually motivated by the use of deep learning for the recurrent neural nets to study time series. So we have, so we can represent. It's actually well understood how to model time series with deep learning. That's where recurrent neural nets were first introduced. And if you look at them, they actually have a couple of important distinct example cases. One is called sequence-to-sequence maps. That's where, let's say, the time series is a stream of words or audio signals. You want to map those stream of words into say, the text, or you want to map English words into Turkish words or something like that. That's what I use. Well, I did Turkish to English when I went to your website. And those are called sequence-to-sequence maps. But the other one, which is the one I'm going to focus on, is to do forecasting. So we have a set of time series. You want to know what's going to happen in the future. And that includes differential equations. Most advanced actually work in this area comes from industry, where the ride-hailing industry, especially Uber and Didi in China, they've done some remarkable papers on using deep learning to study the time series, which describes the traffic and their customers and their transportation. Really amazing. I'm looking at something quite hard: earthquakes and environmental science and COVID. Okay. I actually think the sequence-to-sequence maps, we can actually help to do HPC to devise a whole new set of scheduling algorithms, because there is a methodology called, which I'll briefly mention, called attention, and algorithms such as so-called transformer networks, which are really new approaches to sequence maps. And if you think about scheduling is a sequence-to-sequence map. We have a bunch of jobs, we want to arrange them in the right order. All right. So this sort of takes those words and draws a picture. So the general problem of a time series is this: you have a set of space points. For COVID, the space points are cities, and you have for each point in space, you have some properties of the city, how big it is, what the health characteristics of the number of seniors, the number of people with asthma and things like that. And then you have some time series, which are things like the number of COVID infections and things like that. So, and then we either forecast the future or we do sequence-to-sequence maps. In the case of COVID, we're going to forecast the future. And in the case of that molecular dynamics and Leonard-Jones potential, I just used effectively this architecture here. It's called a recurrent neural net. We have a couple of LSTM layers. These are long short-term memory, which is the most advanced recurrent network at the moment. And that you just feed in the inputs and get out the outputs. Or you can actually get out the sequences to the side. There is this very clever paper called, which describes attention. And attention is a technique for trying to find patterns which match between different time series. And then you find that network, which is the network which gives the best answer for language, you use this attention method to get for these things like GPT-3 and BERT, which are the leading natural language processing systems. For our case here for COVID, we do actually combine both these ideas. We have the recurrent neural network as the final prediction, so-called decoder, and then we have for encoding, we use attention because we're trying to encode the structure of the problem. Because remember, neural nets are so good at finding patterns, so we need to look for the patterns. And this is attention is a very general way of finding patterns. And you just learn, you just form linear combinations of the input data, and you find how they match. And you do that by making queries, which is a linear combination from one sequence, and then you compare it to keys, which are the linear combination of other sequences, and see how and look for overlaps. And then you choose the largest overlaps, and then you feed that, you use that to try to learn how things work. Pretty subtle. And well, this gives amazingly good answers. So here is, I have lots of things like this, but here we have days. So this is running to the mid-August from from January, maybe as we end. So we have a couple of 100 days, and this is we have 314 cities, and this is actually summed over cities. And I have results for every individual city as well, but that's too much to show. And you can see here the orange is the actual data, the blue is the prediction, and the red at the bottom is the easiest one to look at, is the error. So it's certainly not perfect. That's partly because the data is pretty rough, and because people lose data and report it on the wrong day and things like that. One thing that's amusing about these results is that the neural net is a really dumb thing. Namely, it actually produces these giant oscillations. If you look at COVID results, you'll find nobody dies on the weekend, at least very few, not so many, about a factor of 2 reduction. And that's probably a reporting issue, not an actual law of nature. But as we're fitting the neural net to the reported data, the neural net learns that you actually have this weekly structure. Here you see these blue things at the end of the prediction. So it's predicting this weekly structure in the data. And you could, of course, people tell me, oh, well, smooth the data, but we're trying to get the answer. And the neural net doesn't really mind what it's predicting. If it oscillates in weekly data, then that's fine. And in fact, things like ride hailing, they have obvious time structures, which are actually sort of real time structures. These are sort of slightly artificial. Anyway, the neural net will do what you ask it to do. And here are further answers, which even have error bars. You can, in the case of the transformer network, which I'm using, you can get an error estimate from the variation over the attention and seeing which attentions you include. And these are very high quality fits. Here is a somewhat different data set giving similar answers. Here are some So those were summed over the all the data, and also they were normalized in a way that I didn't have time to explain, which was a reasonable way to normalize, but was not real cases. These, I've unwrapped the data and plotted the actual number of cases per day for New York City, and here we have Chicago, which are pretty different. Obviously, New York City was the worst at the beginning, but sort of cured it, got better. Chicago is not so, lasted longer. And you can see it has the weekly structure in both of these cases, and it is in reasonable agreement with the data. Here are some smaller cities. So where King is Seattle, I think, and Los Angeles. So these are somewhat, well, Los Angeles, you can see, is actually starting to peak towards the end of the time. So it's able to reproduce a wide variety of behavior. And so this uses various sophisticated ideas, so-called positional encoding and temporal encoding. You actually feed in, you teach the network what a week is by feeding e to the I theta as the weekly, where theta runs from 0 to 2 pi over 7 days. And also you feed in, you distinguish the cities by properties. So all of these cities have properties. Depending on the data set, we have different number of properties. This is a general feature of these time series. They will always come with properties, and they typically come with properties. In the case here, the properties are the number of beds per person, I said, percentage of senior people and things like that. And so you feed in all those properties. You also have things like measures of social distancing. And you can predict into the future. These particular runs predict 14 days into the future. Anyway, and actually this is interesting. These are all running in Jupyter notebooks with Python, and I happen to use TensorFlow. And I think I should point out that you can use your classical knowledge of statistics. What I fit to is the square root of the number of events, because in the case of deep learning, you usually use these simple things like squared errors, mean square errors, and if you do that, you want to get uniform. You want to get the error estimate correct, and to do that, you take the square root of the number of events, because that has, for counting experiments, that has error of order 1. Okay. So this idea was motivated by work which I'll describe soon with the so-called ML Perf group, which is a very interesting group, and we made a list of possible time series work which you could look at. And I haven't got I don't have, I only have myself and one or two, and maybe a student or two, but so we can't go as far as that. We have my colleague at Indiana's got some marvelous results on using these ideas for predicting the results of race cars, races, in particular the so-called Indianapolis 500. That takes actually real-time data from the cars and uses it to predict results of the races. I'm going to apply it next to hydrology. I'm working on bringing it up now. It's actually quite interesting how these fields are thriving. Namely, there are 129 papers using machine learning in hydrology. That was just in a review which came out, so there are probably more, but this particular review had 129 papers. But I also noted when I read those papers, I don't think they were using optimal parameters, because I had a certain amount of experience, and I felt that they often made the non-optimal choice. And that, I think, is an important issue, that we need to establish some examples of how to do things correctly, because this is a whole new area. The use of deep learning to do surrogates, to do time series, to do big data analysis. This is new, and we need to know which approach works best. And so I'm trying to set up some tutorials which allow one to do that. And I will mention that in the next few slides. And we're probably, I should say we're trying to do the same thing for earthquakes. Earthquakes are a much harder problem because although there's earthquakes of physics, it's not so obvious. I mean, what does deep learning do? It is learning the hidden variables. Well, it's not so obvious there is a hidden variable for earthquakes because earthquakes are, in physics language, phase transitions, and it's not so certain there is a hidden variable for a phase transition. And anyway, so I think we're still looking at earthquakes. It's a good example, again, of time series because you have a set of events labeled by time and magnitude and depth and things like that. And we have some non-trivial answers here, but they're not so good. They're not bad, but they're not as good as one would hope. All right, so now let me come to MLPerf. So I strongly recommend that you pay some attention to MLPerf. It is a group of 80 companies. And here are the 80 companies. It's devoted to developing benchmarks for machine learning. And so there's lots of good reasons to have benchmarks. One is to find out which hardware performs the best. That's the simplest version of a benchmark. But it also can motivate people to develop better algorithms, because if you have published, well-documented results that this data set gives this answer with this implementation, then that will motivate people to do better. And MLPerf, all the data is open, and all the reference implementations are available to use. And so the goal of MLPerf is to try to develop these benchmarks and accelerate progress in machine learning. And it's meant to, it's actually mainly industry. There are 73 companies and 10 universities involved. I'm involved as an individual, not as a university. And there are some people like me as individuals. I just found them one day about a year and a half ago, and I joined their, I mean, actually, there were always some sort of modern approach. They're all virtual. They're just done by virtual working groups. Sort of interesting. And there's an important number here, 50. The estimate is that the amount of effort spent by industry in this area is equivalent to 50 people. So this is a non-trivial exercise. And when you go to their working groups, they're all HPC people, at least nearly all of them, because these are all the people working on the benchmarks. Well, the benchmarks have to be rerunning on HPC. So you see people from NVIDIA who really know how to make their GPUs run real fast. So I find the group of people attached to MLPerf really great people to talk to, really deep, knowledgeable people. All right, so here's just an example page, one you can, which is their version 0.7 of their so-called training benchmark. And if you look at what they have here whatever it is, they have 8 different benchmarks, and they're either images, translation benchmarks for voice, recommender engine, which is obviously a major industry activity. For recommender engines, they're using the reference implementation is a very modern recommender system, DLRM from Facebook, and they have also reinforcement learning for playing Go. And here you have the submissions, and they're sort of pretty interesting submissions. If you go down here, you will find 202,048 TPUs, that's Google Tensor Processing Unit, which actually gives similar performance to 1536 V100s from NVIDIA. And that's 96 of their 16 GPU systems, DGX2s. And you have here they're not all results are present, but they have here results. And you can then look at how they scale with number of systems used, and how you can compare TPUs and V100s. Intel's involved with this, but there are not so many Intel submissions because you need a GPU to get good performance on these problems. So anyway, I have proposed to MLPerf to set up a science data working group, and actually we just started working a couple of, maybe 3 weeks ago. And the idea is to MLPerf, if you saw those applications, they were image processing, language processing, and recommender engines, dominantly industry applications, though actually the image processing has lots of science applications. And even that language, I'm using transformers, which come from the language side of deep learning. So anyway, there's lots of synergy. That's important. There is lots of synergy between industry and science. I never saw this in the past. When we were doing parallel computing, I did not see this amazing feedback between industry and academia about progress in these fields. Whereas today you do get that. You can use the algorithms from industry to solve research problems and vice versa. And MLPerf is really, I've not actually seen a place to get such good interaction between industry and academia. Anyway, so this just says that science data is important. And as far as I know, there is no major benchmarking activity for science data, no general one. And we're trying to address some real problems. The criteria for making a decision is, what would the user see? That's the criteria. And we want to look at both edge systems where you have devices on the edge and sending data back to the center. We want to do end-to-end analysis. Remember I showed you that picture? The machine learning is only part of the problem. So we need to do end-to-end analysis. And we need to look, of course, at inference and training, training the network and then using the network. Things like surrogates, which come from simulations, are not present at all in industry. And as I mentioned, I'm going to include surrogates as one of my major components of this. And these benchmarks, I hope, will help science, because if we put down a benchmark of using time series or using convolutional networks to solve one science data, people will be, and that's well documented with open data and open reference implementation, people can take those and try to improve them either in the original field or in new fields. So I think these benchmarks with the open data, which Mustafa correctly emphasized, are really important in advancing these areas, which are so new that there's no uniform background knowledge which we can assume. So here's, we want to cover a wide variety of science fields. There's some mentioned there: material, environmental, life, fusion, particle physics, astronomy, earthquake, and earth sciences. And I say, I want to try to, I got some funding from NSF and DOE, which will involve building tutorials around these benchmarks. So each benchmark will have a bunch of documentation which allows you not only to run the benchmarks, but understand how to apply that benchmark idea to other areas. We have already identified some science areas. Most of them they either come from DOE labs, or what I mentioned here are some results from the United Kingdom, where my colleague Tony Hay, who I wrote my first paper with him in 1975, so we've known each other a long time. That was when I was at Caltech and Tony Hay visited. But anyway, we're now hopefully going to write papers here on these benchmarks. And they have already identified many important science data, like coming from light sources, electron microscopes, and satellites. But this is just the start. We want to have a bigger collection. And here's just some results of here's an illustration of this cloud masking problem. You have satellite images and you want to identify pixels and classifying them as cloud or non-cloud. and maybe even in detail whether that's snow or sea ice or what have you. This is the project I'm just starting. It actually was approved about 2 weeks ago. And it's called the Surrogate Benchmark Initiative. And it's also going to produce, it also aims to try to take these benchmarks with this open data and make certain they're properly documented with so-called fair metadata, which is, in my opinion, important. And so we have a project to take half a dozen surrogates and to produce them benchmarks associated with those surrogates with the same goals of trying to advance surrogates by having clearly defined benchmarks where the benchmark will be the results of the large-scale simulation, and then reference implementations, which will have these varieties of networks. So like this 2 billion paper, I can't make progress in analyzing that because the data is not uniformly put in one place, and it's not always open, and it's not very well defined. So that has to be solved to be able to make progress. Otherwise, we can't actually say whether the results are correct or not. Well, they're probably correct, how to properly generalize them. Now, an important area, which is what I do, because if you remember, I like building technology. So I'm trying to build, work with especially United Kingdom and also industry on benchmarking technology. This includes this fair access, but also being able to have a uniform method based on Kubernetes, Jupyter Notebooks, and HPC systems to access these data, so that you can gain, or you are trying to make it easier for the users. And if you're interested, please join our effort. Here is, you join MLPerf. If you go to mlperf.org, you will find a place to join working groups, and you just join the science data working group. We'd love to have participants. And we're meeting either once every week or once every 2 weeks. We're making a lot of progress, so we're meeting weekly, at least at the very current instant. So please join us. All right, so the last part of the talk is actually more of the heart of my work, which is building software. And we have a piece of software, 2 pieces of software of relevance called Cylon and Twister 2. And they're all connected with data engineering. They're not connected with running the neural net. I mean, we're trying to help TensorFlow or help Scikit learn by feeding it the data in an optimal fashion and making it easy to build workflows which do that. And there are some challenges here. Now, one challenge is the languages, because you really have to have a world with R, Python, Java, and C++ involved. So we need to have good ways to move between languages, because most of the big data processing is written in Java. Most of the actual analysis is probably Python driven with C++ backends. And so this is, Cylon is meant to be Twister 2 is the data engineering system. It's largely written in Java. Cylon is the system which is the C++ based enhancement with a table interface, because remember, tensors are really just tables. And if we want to use Python and pandas and things, we better do tables well. And so Cylon is the interface that makes links the data engineering to the data science. The data science is the TensorFlow, and to the notebooks. So that's sort of explained here. And over here is yet another plot showing how these three aspects of the world are joined together. We need the data processing, that's all big data processing, Spark, Flink, Hadoop, Storm, R system, Twister 2, Dask. We have the machine learning system, which is PyTorch, TensorFlow, and so on. We have these different programming languages, and we have these data formats, Pandas, HDF5, and we use Arrow and Parquet. These have come from Apache, and are really good for doing vector data formats with very high interoperable performance. And we, of course, need to drive everything into NumPy, because NumPy is the critical data science engine. And this here we have this picture which shows the problem we're trying to solve. We have raw data, we have Jupyter notebooks, we have training, we have inference, we have all this data engineering which sort of surrounds this thing here. And then, of course, we have some output. So we're trying to enable this system to work. And so the data engineering is, we can think of as trying to make these tensors and these NumPy arrays where we extract in classical ETL industry fashion data from data lakes and repositories and things like that. And so here's a nice picture which really shows graphically what we're trying. I would say there are clearly two big data ecosystems which are very important. One is the one that gets the most publicity because it's so exciting. It is the machine learning system and the deep learning system. We have all Python, PyTorch, Keras, TensorFlow, DAS, Rapids from NVIDIA, Pandas, and NumPy. Then we have the actual, where most of the previous work went, is the Java-based big data processing, Hadoop, Flink, Spark, Twister2, Storm. We work a lot with Apache Beam, which is Google Cloud Dataflow. And we must link these two systems together. So this is the data engineering, this is the data science. So we have to get both to run with high performance, and we want the link to be high performance. And Twister2 is the system we built along maybe a year or so ago. We started about 4 years ago. And it's linked to Apache Beam, which is the basic data processing framework, which has got a lot of important capabilities. And it basically, like Spark, has lots of operators, and it has things like RDDs, data sets, and things like that. And it supports data flow operations. They're all written assuming we have a data flow world. Then Cylon comes and maps this into these high performance operators, which are C++ based. So you do your data engineering with the technology you know, and you do your data science with the technology you know, and you don't lose by going between them. You can look at this, I'll leave this in my slides. You will see that Twister2, because it has HPC built into it, Twister2 was basically, crudely, Spark re-engineered to have HPC. It was redesigned from scratch with HPC as required in all operations. And it outperforms Spark with non-enhanced Spark in all machine learning. And for things which aren't machine learning based, so aren't so performance sensitive, it does as well as Spark. So this just states what we're trying to do. We're trying to get high performance data engineering in Cylon. And this is the architecture. We have these table APIs. And we have, and they are mapped into C++. And then you have your basic operators, which are going to run with very high performance to do unions and joins and differences and all-to-all, broadcast, all these classic algorithms that you need. So Cylon was just released. It seems to already be pretty popular. It's written in C++. It uses Parquet, which is the format from Apache for storage and in memory, Arrow and Parquet. And we are gradually improving the way it links with Pandas and NumPy and the Pandas and NumPy can link to the Spark type world. Cylon works fine with Spark. It also, of course, works fine with our own system, Twister2. So here is the performance results. I wouldn't be dare to carry on unless Cylon wasn't the best. This is a join operation, one of the standard operators. We have Spark, Cylon, both of which is PySpark, which is using Arrow, this green one. And here we have Modin, which is a famous, really well-known system. It doesn't work so well. We have sequential pandas up here. We have DASK, which also doesn't work so well. So these important systems, and just note, they do not scale parallelize properly. So we need to have good parallel performance for these data engineering operations, and Cylon is designed to do that. Here is different languages, again, against the number of processes involved, and we have C++, Python, and Java-based front ends. And you can see that there is little overhead, and they all perform quite well, especially for large number of processes. This is again for join. So you can invoke the join from Java and not get the biggest overhead you get here is about 10% for 16 processes. And the last plot I have here is very large systems, again an inner join. And if you look at the ratio between PySpark, so here Cylon is even better, higher performance than Spark. So it's Cylon is about 4.5 times faster than Spark on the larger system, and on the smaller system it is twice as fast. So Cylon has, because it's not surprising as fast, it's built from the scratch to only care about performance. So as I say, high performance in computing is really important. And if you look at these commodity worlds, Java and Python, they're not high performance. So there's lots of exciting work to be done building performance into these systems. And here it just points out we can do Jupyter notebooks, and we want to link properly. We haven't quite got these engineering quite right yet, but we will soon have Jupyter running very well with Cylon. In fact, I think Jupyter notebooks need more attention. There's not so much work taking Jupyter notebooks and linking it to HPC systems and things like that. There's some, but there's not terribly done systematically, and there's no clear consensus as to how to do it. But obviously we have to do that. Jupyter Notebook is such a nice environment. And all my work I do at the moment is with Jupyter Notebooks. All right, so we're trying to, these are things we're going to be doing. Rapids and CUDA here, or data frame, are the NVIDIA efforts. We need to take a table API to a data API, which will support this well-known system called Modin. We want to work with DAS, which is the Python multitasking system. And there's an HPC product called UCX, which will enhance our communication. And basically, we're trying to get each ecosystem. Twister 2, if you like, is the big data ecosystem done well with HPC. Cylon needs to both link that to the Python interface and Python ecosystem and make the Python ecosystem run fast. And we're also trying to increase the number of applications we do. This is not useful unless we have applications. And let me skip that. So here's the final slide. And so I think parallel computing and HPC is incredibly healthy. It's essential to make progress in this field. And we have deep learning and surrogates giving us lots of new challenges. We have this machine learning for HPC and HPC for machine learning. You could say what I was doing with Cylon is HPC for machine learning. And we need to support this total switch of, if you look at over the last 5 years, classic machine learning is being replaced dramatically by deep learning. Like in MLPerf, it's called machine learning performance, but actually everything in it is deep learning. That's because all the leading edge algorithms in industry are deep learning. And there are lots of new algorithms in science that we developed. I mentioned some time series work, which I happen to be doing. And then we have these surrogates, which are important. And we also want to produce tutorials around these benchmarks. I think we should all collect. industry is really doing exciting work these days. We need to have more interaction between industry and research, and HPC, academia, and ML Perf and ML Sys communities. And we need to actually have a little better understanding of data engineering and how it compares to data science. I think data engineering is pretty important and needs more attention. And I showed you how Twister 2 and Cylon can give you the advantages of well-known systems like Spark with a better attention to HPC and deep learning. And I have here the last slide, just lists some of my collaborators. Gohan is in the audience. He's been actively working on Twister 2. And Ahmed from my times at Indiana, well, I mean, when he was my PhD student, he's also helping us there. So, and we have lots of external collaborators and things. So thank you very much. That's it.
Okay, thank you very much, Dr. Fox. It was wonderful talk and it was very good. We have some questions, but before our Minister of Science and Technology, you have any question, or just because? Thank you very much. You all attended all the talk, and it was.
Oh, for Mustafa, I tried to make the case that his industry and academia really need to work in this area. Compared to when we were in Indiana together, the collaboration between industry and academia is much more important and much more fruitful today than it used to be.
Definitely. I will try to learn Cylon. But it's hard for me. I'm very out of this high-level science. So, but I will encourage our institutions to join the benchmark program. Maybe we can contribute. We can support some of the students, some of the researchers to contribute your work. I will definitely take a look at the Cylon data engineering and data science is important. So I will take a look at the Cylon.
Thank you.
Thank you so much. It was a pleasure. So I hope when you visit Turkey, you can also come visit me, or we can get together.
Yeah, we'd love to do that. Yes, it would be marvelous to get together again.
Okay, thank you so much.
Thank you.
Thank you very much. We have some questions, Dr. Fox. Also, before doing that, you have a mention about some sample for car race. It was very interesting to deep learning and image process. Can you explain about a little bit? It's my question. It was very interesting. Because the car is going very, very fast, then a real-time data, because the speed also is very important. How the management to track the car race and to find the result. It was very interesting to find who is the winner, I think, or something for.
Yes, so you have to
HPC, yeah.
So that's my colleague Judy Chu, and the challenge actually is that you have to learn about pit stops, because the critical in these car races is that the cars have to decide when to change the tires and when to add gas to the car, and then there's a drastic change in the order, and so you have to effectively learn that. And the data, actually, there's a huge amount of data from these cars. They have data up to, I think, 100 times a second coming from every car. They have data from the track and data from the car. And that's all fed into the LSTM network.
Okay, thank you. Yeah, we have many questions. I would like to start from the first questions. Actually on the chat session, but I can read the questions.
Let me see. I have the chat. Which question do you want?
Kemal Ebcio, the first question. Did you see it like a very good talk? And as an experienced researcher in deep learning and supercomputing, do you see limitations regarding to the future potential of artificial intelligence and deep learning? And what is it that deep learning supercomputers will not be able to do? The first question. I try to read it, but can you see also the question?
So this is the question about, so it's, as far as I know, nobody quite knows how powerful these surrogates are. This is a question about surrogates. And I see that's a very important research issue to try to understand when surrogates work and when they don't work. And so that's what I'm trying to do at the moment. I mean, the two areas I'm working on at the moment are, apart from Cylon, I have time series. I'm also working on trying to develop the methodology for surrogates, because the surrogates are very fruitful, but they've been applied just individually by lots of different people. And there's no clear consensus as to what the right network is and how to do it best. So I think there's a lot of research to be done in that area. But I think the parallelism is clearly thriving. I mean, this whole industry revolution we're looking at only works because of parallel computing. And if you looked at the ML-Perf results, actually some of the speedups are not always so good. And I think there's probably work to be done in improving the speedups of parallel deep learning.
Yes, thank you. And another question from Fadishar. Very interesting talk. Thanks to Professor Fox. I would like to ask about the open challenges in the field of machine learning HPC that researchers need to focus on in order to advance the research of this field and move it forward. Just a summarize about these challenges is appreciated. Thank you.
So the challenges on the interface of HPC and machine learning. So, well, actually, I think parallelism. If you look at parallelism, there are lots of different sources of parallelism. You have data parallelism, model parallelism, pipelining parallelism, and to try to understand which parallelism is working best in each circumstances, it needs more work. Typically today, parallelism is all data parallelism. If you go to ML-Perf, they are running in parallel, but they're doing data parallelism. Namely, they're replicating the model, they're taking the model and just chopping the data into different parts, running those parts separately and joining them together, which is the trouble with that model is that due to the stochastic gradient descent, you don't want to get the batch size too big. And so if you chop up the problem, the batch size, the thing you're chopping up is the batch. And so what you end up doing with data parallelism is increasing the batch size. And that will then actually make the thing converge less well. So there's an important question about how you do the parallelism and so it's an algorithmic HPC trade-off. I mean, and the reason why you don't do model parallelism doesn't have that problem, but it's pretty difficult to do because you actually have to do classic parallel computing, because if you chop up the model, then you're going to have to communicate things between processes and things. That's actually pretty much like parallelizing a classic scientific simulation. And the original paper was actually done at Indiana University by a fellow called Adam Coates, who was visiting at the time, who was Andrew Ng's student. He did model parallelism, but very few people have done model parallelism since then. Because it's just, these networks are so large, they're changing so fast, we don't have automatic methods for doing it. So that's a challenge. There's also this interesting pipeline parallelism, namely, if you take a classic deep learning network, it's actually a set of layers. And you can actually chop those layers up and do them in parallel. You can pipeline it in parallel. So a particular processor only does the first 3 layers. The next processor does the next 3 layers and so on. And there's some papers from Microsoft and Google in that area and other people, but I don't think the results are actually even necessarily correct. We can't reproduce some of their results. And but it's sort of interesting because pipeline parallelism is not present in the scientific simulation. But it's clearly present because of this layered structure. I mean, it's a remarkable feature of these networks. I mean, these things, some of these networks like ResNet have 200 layers or more. And so there's quite a bit of potential parallelism there.
Okay, thank you. Then is another question from your student, Beytullah Yıldız. Dear Dr. Fox, I am so glad to see you again and thank you for giving this wonderful talk. Can you suggest us research topics that will be popular and need to be solved in HPC deep learning fields for the future studies? Secondly, you talk about the attention mechanism. What do you think about the statement of attention is all you need? Waswani article.
Yes, so that's what the transformer network is. Attention is all you need.
Yeah.
And I would not agree with that assertion in that I think, you see, they're doing sequence to sequence. That paper is looking at natural language processing with sequence to sequence maps. And it is also doing sort of a classification problem. You're trying to take audio signals and classify them as words. Well, if I do time series of any type, I'm not. It is sort of classification. We're classifying things as numbers, but it's better to think about it as a numerical operator. And I'm not convinced. That's why I used when I used the transformer to describe COVID, I used the classic LSTM to do the final step. I used attention to find areas of interest which should be looked at, and then I fed the things found by attention into the LSTM network for the decoder. So I think it's more complicated. I think attention is very important. I'm actually thinking that maybe for earthquakes where we don't have so much scientific progress, it might be attention is especially important. But I think it's all, as far as I know, that's a completely open area. There is very little papers in this field. The number of papers on using transformer and number of papers on using attention in scientific problems is almost zero. Because it's really been devoted, it's really a lot of work in the language area. Now, you also asked about general problems. I think the whole problem of how you make Jupyter notebooks or general notebook style programming, which is very attractive to users, how you interface that with HPC systems is really wide open.
Okay, thank you for the answer, Dr. Fox. There's another question, again from your PhD students, Hassan Bulut. I would like to personally and also on behalf of my colleagues, thank you for your inspiring presentation. Many thanks for steering us in the right research direction. Your ideas are utmost valuable for us. My question is, when we think about the intersection of HPC and machine learning, the first thing that comes to mind is to speed up to improve the accuracy of ML algorithms. However, I wonder how HPC or distributed systems paradigm can help ML to introduce new, almost fully distributed novel algorithms. I mean, how can we utilize HPC features to exploit the potential of distributed machine deep learning algorithms, not just making today's algorithms or frameworks work on parallel infrastructures?
Not quite certain what the question is. So, I mean, I tried to point out that the opportunities in parallel machine learning were very high and not fully described, because the thing that I started working on, which I now realize was a little too naive, was just doing classic parallel computing on the machine and in the linear algebra kernels and things like that. And there's quite a lot of work which is harder on parallel algorithms for graphs, because the graph algorithms are very difficult to parallelize. But deep learning is probably more important, because so much of the work today is deep learning based. And I would consider that that's not well studied. Deep parallelism and deep learning. There's some, I might say, it's all data parallelism today. Or if you look at all the ML perf results, every single one of them is data parallel.
Okay, thank you for the answer. Another question from Kemal Ebcioğlu. Another question. You discussed using supercomputers for speeding up some applications with the great amount of inherent parallelism. What are your thoughts on the speeding up unstructured, sequential natured applications? Can we envision parallelizing such applications at supercomputer levels?
Well, you have to give me an example. Give me an example of such a problem, because I once wrote a paper saying every problem is parallel. A book, actually, I wrote a book saying that. Was a long time ago, so it may not be correct, but there aren't so many sequential problems in life. I say deep learning, I mean, all these AI problems, even graphs are parallel. They're just difficult, but they're still parallel. Unstructured, he mentioned. So the unstructured makes it hard. I mean, unstructured problems are the hardest to parallelize. And that's been true both, that's true whatever the problem is.
Hi, hi, this is Kemal.
Yes.
I was really asking about unstructured applications. For example, SpecInt. I mean, that's a general purpose application, and it's representative of much that's going on in systems or even operating systems. So I mean, general. What do you think about
that
problem of parallelizing sequential code?
All right, so those codes, I mean, well, of course, there's a couple of things you could come with them. One is, we all know the work on parallel compilers. I used to work on that with Ken Kennedy from Rice University, unfortunately died, but the progress in automatic parallelization is still relatively limited. You can parallelize particular domains, but something which is hard to parallelize is, say, operating systems. And I'm not certain that that's going to change, because those are very asynchronous. What I do think you can do is, I think machine learning is able to get big speedups, because machine learning doesn't matter, it doesn't care whether it's asynchronous and things. It can just learn the answer. So it can replace a set of complex operations by an answer, which it just learns. So I would recommend looking at effectively producing a surrogate, an operating system surrogate, which is machine learning based.
Thank you very much for that excellent talk. Thank you very much.
Thank you very much. Is there any other questions? And actually, we have many questions, then you answer the questions.
I should just again emphasize what an honor it is to see all my friends again. It's amazing how Zoom, I can see people's pictures who I remember.
Yes.
Ahmed Sayed looks like he always used to look. So do you, Ahmed. Both Ahmeds look pretty much the same as they used to look.
Yeah, thank you. Also, you too, same, Dr. Fox, and you have very good energy and like a research, and you give us guidelines and research opportunities. Actually, very promising, and we are very, very happy to have in our conference again. I hope in another conference we will be free of COVID, and you will be all together in Turkey and in Istanbul and in Ankara, very different places. I hope so. And
yes, so do I.
Yeah, thank you very much for your valuable time. You know, we are all together, and we are very enjoyed being together. If you don't have any other questions or any other issues, just I'd like to close the session today. Actually, we'll continue tomorrow also. Tomorrow in the morning, Dr. Ömer Rana, also you know him very well, from Cardiff University. He will have a talk tomorrow. And another faculty from Indiana University at 1:30 p.m. Mehmet Dalkılıç, also he has a talk. And like a two from Indiana University, one from Cardiff, UK. Then we will continue our session tomorrow also. We are finalizing our sessions today because of the time difference. We want to invite you during this time. Again, thank you very much for joining our conference, and we are very glad to be see here. And thank you again.
Yes, it's an honor. Thank you very much.
Okay.
Thank you, Professor.
Thank you.
Thank you.
Before leaving, maybe I can talk about tomorrow's sessions. If you want, again, very short time, if you allow me to share the screen. Okay. Actually, what we have tomorrow, like a starting 9 to 10, Professor Ömer Rana from Cardiff University, UK. And our sessions will continue at 10 to 12:30. And we have a break. Then after, in the afternoon, Dr. Mehmet Dalkılıç from Indiana University as a invited speaker, our invited speaker, he will have a talk. Then we will continue our presentation between 2:30 to 5. Again, thank you very much for attending the sessions. Again, I hope you have a very good day. Thank you again.
I posted a link to my presentation in the chat.
Yes, it's wonderful. Then we can also put our own website as a link.
Yeah, you're welcome to put it on the website.
Okay. Thank you again, because there were some questions. I see it here. The link. Okay. Thank you and have a good day.
Yes, I will.
Okay. Bye.
Thank you. Bye.
Bye.